Bismillah ar-Rahman ar-Rahim. So let us complete what we have started. We will solve another problem, but this one is a little bit more dense and have more details than the previous ones. So let us read. Consider a linear system with impulse response e power negative t multiplied by u of t minus 0.5. This is the impulse response of the system. The linear system itself, the input is g of t equals w of t, which is the noise signal, minus sine 6 pi t plus pi over 3. W of t, as we have just mentioned, is a noise signal, and its power spectral density is as follow. This is a triangle function, this delta. Okay, and we will see how we will draw it just right now. We would like to solve A, B, C, and D. He's asking for the total output power of the linear system, power caused by the sinusoidal input only, and for the power caused by the noise component only. Then he wants to know the output signal to noise ratio, which is the SNR in decibels. So this problem is a very great opportunity to practice these topics since it is a comprehensive problem. So first of all, we had a hint in the homework to convert the sinusoid into a frequency domain, the same as noise. So we would like to convert sine 6 pi t plus pi over 3 to the frequency domain. So we have seen in the lecture that when I have a sinusoid with this form, I convert it into frequency domain by doing so. I get the amplitude, which is the value multiplied by the cosine of the sine. I power it and divide it by 4. Then I multiply it by two terms. Delta, f, which is the frequency, is my variable, minus fc plus delta f plus fc. So what is fc? fc is I get the input angle in the sine or the cosine and divide it by 2 pi, then I will get the fc. For example, I have here the input is what? 6 pi t, sine 6 pi t. So here 6 pi will equal to what? 2 pi f. So my f will be equal to what? My f will be equal to 6 pi divided by 2 pi, which is equal to 3. So here my f is equal to 3, my fc, and I will just plug here instead of the fc, I will plug 3. Moving to the next part. Now, so far I have converted the sinusoid into a frequency domain, and the noise was in a frequency domain from the start. Then my target is to calculate the magnitude of the system frequency response, because it will be used a lot in the power calculations. So in order to get this term, what we will do, first of all, I have to transform the system response from being in time domain as it is here to frequency domain. So in the Fourier transform, we will find that when I have an element e power negative a of t multiplied by u of t, its Fourier is 1 over a plus 2 pi f j. And since this is not the exact case in our system is shifted. Here the a is equal to 1, yes, while the t is not alone, it's shifted by half. So its Fourier will be equal to what? 1 over 2 plus j2 pi f. Why have I added here 2? I have added here the reciprocal of the shifting agent. Okay, so far I have the h of f. This is the h of f. Then I would like to get the magnitude of h of f. So how do I get the magnitude? I just get the power of the denominator separately. So 2 power 2, it's 4. I put a plus. 2 pi f power 2, it's 4 pi square f square. So I don't take j into consideration. So j square, I won't square it and make it equal -1. No, I will just remove it from the term. I will square 2, it will be 4. Square 2 pi f, it will be 4 pi square f square. So this is what now? This is the magnitude of my system frequency response. So how to obtain the power to obtain the power, we would like to get the integration from negative infinity to infinity to the magnitude of the system response multiplied by what? Multiplied by the signal in the frequency domain. As we have done here, this is what? This is the magnitude of the system response. This is h of f squared multiplied by the signal. My signal is consists of noise, which is a triangle function, f of divided by 4, and what? The sinusoid. Okay, so moving to part B, where I would like to calculate the output power of the sinusoid part. As we have just mentioned, we will make an integration from negative infinity to infinity. We multiply the magnitude of the system response frequency domain by the function of the sinusoid, which is formed by the Dirac delta function here as follows. So we would like to we will substitute with the magnitude with this value that we have just obtained. I have taken 1 over 4 here in the term of the delta's output as a common factor in order to take the constant output to facilitate the complexity and make my life a little bit easier. And then I would like to perform the integration. I will integrate the first part, then I integrate the second part. Since the magnitude is multiplied by both of them, so I'll just multiply it by both of them so that I don't forget it. So this is my integration. This is the first term and this is the second term. Then we would like to remember something from the signal course, which is what? The integration of the Dirac functions, the shifted one, with another function. We just don't integrate. This is in the case of integration from negative infinity to infinity. We don't integrate. Simply what we do is that we take the coefficient here and substitute in the function. So let me say it in another or in a more clear way. My function here is 1 over 4 plus 4 pi square f square, and it is multiplied by what? It is multiplied by the Dirac delta function minus fc, which is 3 here. So what do I do when I do the integration? I take this function and substitute instead of f by 3. This is what I've done here. I remove the f and substitute by 3. And the same here, I remove the f and substitute by negative 3, since here is f plus 3, not f minus 3. And I just I remove the integral, since what I'm doing now is the integration. This is a special case for the Dirac delta function. And I obtain the values, added these two terms, same denominator. So the numerator we will just add it, 1 plus 1 equal 2, multiplied by 1 over 4. So the total or the final value of the power is as follows, which is 0.00139. Okay, what? So this is the power of what? Of the output caused by the sinusoid wave. Okay, we would like to move to the power due to the noise part of as the input. So we will just revise what is the noise part as the input. We have just mentioned that it's a triangle function of f divided by 4, and the rule we mentioned that we multiply this function by the magnitude that we have obtained. Then we would like to integrate it from negative infinity to infinity. So first of all, I wanted to draw this function and check with you how to draw it. We have a xy plane. The x has the frequency and the y has g of f, which is a signal or the magnitude by substituting of f. And triangle, it looks just like this. Triangle, where its 2 points are the point below the frequency divided by 2. Since this is f of over 4, so I take 4 divided by 2. So it's between 2 and negative 2. And its peak is what? It's 1. It's always equal to 1 in this case, since I don't have any number multiplied by it. But however, if I have 2 delta f divided 4, we would like to get the integration of this function. And as we have agreed before, the integration is what? The integration is the area under this function. So the integration will be this area. The area that I am shading here and this area as well. So instead of getting this function and getting this function to integrate both of them, this one from pound negative 2 to 0 and this one from pound 0 to 2, we will do another idea or a more smart one, which is integrating from 0 to 2 of this function only. We will remain it g1 of t. However, we will multiply it by 2. Why are we doing that? We are doing that since this function is known to be symmetric. The area here, for example, it's area 1, it's always equal to area 2. Why is that? Because it is a symmetric function. So instead of getting two functions and waste time in getting the equations of the two functions, we will get only the equation of one function and integrate it, and the output of the integration we will multiply it by 2. However, I must be careful with my bounds. My bounds are here from 0 to 2. Since I decided to get this function and multiply it by 2. If I decided to get this function, my bounds will be negative 2 to 0. So, moving forward, we want to get the equation of this function. The equation, to get the equation, we have to get the 2 points. And the 2 points here, we choose to be 2 and 0. And 0 and 1 here. We get the slope 0 minus 1 over 2 minus 0, which is multiplied by f, which is the variable here, since we are in the frequency domain. So it is negative half f plus c, which is the intercept with the y-axis. Since this intercepts y-axis at point 1, so c will be equal to 1. So this is my function that I will integrate, and I will multiply it by the magnitude. So here, the integration of the triangle function over the magnitude is multiplied by the magnitude, but since it's a fraction, so here it is as the denominator. So I just replace the triangle function with this one I have just obtained, and as we mentioned previously, we multiply it by 2, as I want the area under the triangle, not the small triangle. So I have this term, I would like to integrate it. So as I have just mentioned previously, we will split it into two terms. 2 is taken as a common factor. This is the first term, negative f of 2 over these terms. And the second term is this one, 1 over this term here, as I have done here. And here I have done also another thing, that I have taken negative 1 over 2 from negative f of 2 as a common factor here. So it is negative 1 over 2 integral f of 4 plus 4 pi power 2f, and here it's plus 1 over 4 plus 4 pi power 2f. Moving to the next step, which is the integration, how to integrate this part. What I have done here is I entered the 2 on the two terms again. These steps are not obligatory. You can just keep it outside or inside. However, I found that I have here negative half, so I wanted to multiply it by 2 and cancel it. So 2 times negative half, it's equal to negative 1. 2 times 1 here, it's equal to 2. So this is my new case. I would like to integrate this part. So integrating this part, it might be a little bit difficult, because this function need to be known previously. However, this function is integrated to be a len function. Why? Because when we differentiate len function here, when we get to differentiate it, we differentiate the part inside the len function and divide it by the whole function itself. So the part inside this function is 4 plus 4 pi square f square. Its differentiation is 4 pi square multiplied by what? By 2f. Divided by what? Divided by the function here itself, which is 4 plus 4 pi square f square. We say that we differentiate the angle or the items inside the len function itself. These are the ones inside the function. The differentiation is 8 pi power 2f, as we have done here. We differentiated the f square. It is the only variable, which will get 2f multiplied by 4 pi square. So the total is 8f pi square divided by what? Divided by the function inside the len, which is 4 plus 4 pi power 2 f power 2, as done here. So why am I saying all this info, or why is the hassle? Because if I focus here, I will find that this term is a little bit familiar. This one is a little bit familiar to this one. However, it requires two terms. It requires 8 and pi square, so that this is exact. So in order to get this term, we multiply here by 8 pi square and divide here by 8 pi square. so that I can complete the integration problem as I've done. Okay, moving to the second part, I have here 1 over 4 plus 4 pi square f square. Also, this is an famous integral, which is similar to what? I have function called tan inverse x. When I get to differentiate it, it gives me what? 1 over 1 plus x squared. How do I differentiate it? I get into the angle here, x, and differentiation of x equal 1. So I put here 1. Then I divide by what? 1 plus the angle power 2. 1 plus x power 2. So here, if we look, we will see what I have here 4 plus 4 pi square f square. So I decided to take 4 as a common factor to make my life easier. So it's here, it becomes 2 over 4. This is 2, and 4 is the one that I have just taken common factor. So the remaining part is 1 over 1 plus pi square f square. Okay, moving to the next part, I am having this term. This is the term I'm having, and I want to integrate it. So how would I integrate it? As the same way I've just mentioned. My function here, 1 over 1 plus pi square, I can change it a little bit or manipulate it in order to get me the differentiation of tan inverse. So let us see if I have tan inverse pi x. How is it differentiated? Its differentiation equals to pi over 1 plus pi square x square, which is the same case here. However, I don't have upside pi, so it's a little bit easy. I'll just multiply by pi above and divide by pi here at the lower. And this is what I've done. Multiply by pi and divide here by pi, and here, as I've just stated, about the 8 pi square. So I am ready now for the integration, which I will be doing here. This will be ln 4 plus 4 pi square f square, and this will be tan inverse pi f. What will be done now is a substitution by the 2 pounds here by 2. 4 plus 4 pi square f square, which is 2 square, which is 4. So it becomes 16 pi square minus substitution with 0 minus ln 4 plus 0. This is the first one. The second one is tan inverse 2 pi minus tan inverse 0. So here for simplification, let ln 4 plus 16 pi square minus ln 4. If this is x and this is y, the total will be ln x over y in one ln. And 4 plus 16 pi square divided by 4, it's equal 1 plus 4 pi square. We divide them. This is the first term after being integrated. However, the second term is what? It's tan inverse 2 pi minus tan inverse 0. Tan inverse 0 equals 0. And tan inverse 2 pi has a value. We mustn't forget the constant that we have taken common factor or outside the bounds, the integral. We take them into consideration in our calculation, add these two terms, and then we will get the power of the noise in what caused by the power of the power at the output caused by the noise at the input. Part D, he wanted to calculate the SNR, which equals 10 log B output over P noise. This is the formula. So we will get 10 log. Always when he doesn't mention log what or to the base of what, the base is directly to the base of 10. So this is log to the base of 10. P output, it's this value we have calculated at first. This is part P divided by P noise. We have just calculated 0.178, and the result will be in decibel, which is negative 21.074. The log is evaluated on calculator. It's not evaluated by mind, especially with these decimal values. And that was our problem for today. However, in part A, he wanted to get the total output power. So in this case, we will calculate or add the power of the noise and the power of the ordinary output. This will be the total power. This is a good question. Just take it into consideration because it's comprehensive and covers a lot of topics. Thank you for your listening and good luck in your exams.